Alright guys, let's work on some exponential functions and their applications. So what we've been working on in the past are algebraic functions. Algebraic functions are something where the variable is the base, like x to the 4th power. But what we're going to be focusing on now are called exponential functions, and that's where the variable is in the exponent, so something like 4 to the x. So I really want you to get the difference in what we've been doing and what we're going to be doing now. Whenever you're trying to evaluate exponential functions, you still work them the same way. You put your value, if this says find f of 1/3, you put your value in for the x. By the way, that's supposed to have an f right there. Sorry about that. Okay, so if we want to find f of 1/3, we say 4 to the 1/3 power. Well, what does a 1/3 power mean? Remember, that means cube root. So this is the same thing as the cube root of 4. And this can't be simplified any further. So that's pretty much all you can do with that one. So what if we want to find g of 3? This is the function g, so we put 3 in for x. We have 5 to the 2 minus 3. 2 minus 3 is -1. And remember, -1 as an exponent means you find the reciprocal. So you have 1 over 5 to the 1. Well, what if you want to find h of -2? Here's the function h. Put -2 in for x. We have 1/3 to the -2 power. Remember, a negative power means to flip it over, so that would give us 3 over 1 squared. Once you flip it over, then the exponent becomes positive. Well, 3 over 1 is 3, and 3 squared is 9. So that would be 1/3 to the -2 power. So how about number 4? Find f of -2 and f of 1/2 if f of x is 9 to the x. So they're changing the function on us. Now f of x is 9 to the x. They want us to find f of -2. So that would be 9 to the -2. They also want us to find f of 1/2. So that's 9 to the 1/2 power. Well, 9 to the -2 means 1 over 9 squared. And 9 squared is 81. 9 to the 1/2 means the square root of 9, and the square root of 9 is 3. So the graph of an exponential function looks like this. It starts off really low and really slow, and then all of a sudden it shoots up and goes up really fast. Have you ever heard someone say the population is growing exponentially? Well, that's what they're talking about. The population started off low, it started growing, but it wasn't growing very fast. But once it did start growing, it shot up like crazy. So it's growing exponentially. That's what that means. If we were to graph this 2 to the x, by the way, in the future I'm going to call this the parent function. So all exponential functions I'm going to compare to this one. If I were to graph this using those methods I taught you on the previous slide, then you would come up with this graph. What is the domain of this graph? All of the x's are the domain, so that would be everything, right? -infinity to infinity. How about the range? The range looks like it's starting at 0 and going up, but does it include the 0? Does it include the 0? Well, can you have 0 equals 2 to something? Is there anything you can raise to get 0? You can't, right? So it's never actually going to reach the 0. That means we do not include the 0. You can think of this kind of like an asymptote, but that's not what we're going to call it right now. So it never actually reaches 0. Alright, so what if we change the base? Let me go back for a second. Here the base is 2. Here the base is 10. So if we change the base from, remember the parent function is f of x equals 2 to the x, what happens to it? Well, you can pause the video and calculate these if you like, but this is what the graph looks like. I want you to compare that to the one on the previous page. See how this one is kind of wide, not very steep, more rounded in the middle? Alright, look at this one. We have more of an L shape. It's a little more pointy here. It gets steeper faster, and it's actually closer to the origin, closer to the x-axis. So that's what happens when you change the base to something bigger than 2. It makes this taller, so it makes it steeper faster, more L-shaped, and closer to the origin. So let's just say it's more L-shaped. It just means the corner is not as curved, or it's more of a curve, I guess you could say. And then it gets steeper faster. Okay, what's the domain? The domain is still everything. What about the range? The range is still 0 to infinity. So what about if you put a fraction here? Remember the parent function. We're going to keep going back to that one. The parent function was this one. Compared to this one. What happened? It reflected it, right? The original function was something like this. Something like that. Well, all it did was reflect it over the y-axis. Well, have a look. Isn't this the same thing as 2 to the negative x? Remember, the negative exponent means find the reciprocal, or flip it over. So if your exponent is negative, that means the negative is inside the function, right? Remember when we were talking about transformations? That's what we're going to be doing now. So if your negative is inside the function, it's going to reflect over the y-axis. Right. The base is still the same, so it doesn't get steeper or more L-shaped or anything like that. All it does is reflect over the y-axis. The domain is still everything. Amazingly, the range is also still 0 to infinity. Alright, so this time we do have the negative inside, which makes it reflect over the y-axis. But what does this 3 do? The 3 makes it more L-shaped and steeper faster. The domain is still everything. The range is still 0 to infinity. So now we still have our same base as the parent function. But what did we do? We subtracted 3 inside the function. Remember, if it's inside the function, it shifts left or right, and it is opposite of what you think. So we took that parent function, which did something like this, and we shifted it 3 units to the right. Okay, the domain is still everything. The range is still 0 to infinity. How about this one? This one's a little more complicated. So we change the base, compare it to this one. We change the base from a 2 to a 3, so it's steeper faster. It's more L-shaped. What about the plus 2 inside? The plus 2 inside makes it go left 2. But what happens when you subtract 4 outside? That makes it go down 4. So if you compare that to the parent function, which was something like that, you can see it is a tad bit steeper. It is a little more L-shaped. It's shifted 2 units to the left and 4 units down. Now the domain is still all real numbers. But what about the range? It was 0 to infinity, but it shifted 4 units down. So now it's -4 to infinity. And you don't include that -4 because you didn't include the 0 up here on the parent function. Okay, how about this one? We do have, let me write this again, f of x equals 2 to the x. We do have a bigger base, so it's steeper faster and more L-shaped. And then what else do we know? We have a negative inside the function, so it will reflect over the y-axis. We have a negative outside, so it will reflect over the x-axis. And what do we know about multiplying a function by a fraction? Remember, it stretches it horizontally. So you could say stretches horizontally. Makes it short and fat. Or you could say it compresses it. So it makes it really short and fat. That's what that one is doing. So how about the domain? Still everything, but the range. This time the range is upside down, right? It was 0 to infinity. Now it's negative infinity to 0. Okay, how about this one? We have a bigger base. Bigger base means steeper, faster, and more L-shaped. Negative inside the function means reflect over x. Negative outside means reflect, that means reflect over y. So negative inside the function means reflect over the y-axis. Negative outside means reflects over x. The domain is everything. The range is negative infinity to 0.